wait, so the last, like, cause I missed the last one, so.
There has been nothing posted from Tuesday yet. I
Okay.
will do my best to have that posted this afternoon. So yeah, I didn't post any lecture or any whiteboard notes on Tuesday's lecture yet. So I'll
Okay.
try to do that this afternoon. Basically, we studied what's called Newton's method. And we're going to do another example of that today. In fact, we're going to do that right now. So last class, we introduced Newton's method. So he didn't invent it, but he gets the credit for it. So what is Newton's method? What it does is it's a method for approximating solutions. All right, let me not say solutions. Let's kill a couple birds with one stone. What it's really, the way you think about it, because of its geometric interpretation, it's a method for approximating roots. So if you remember, what is a root? A root is a solution to an equation. That's one way, or it's the place where the graph crosses the x-axis. So let's do an example of that. So consider let's use Newton's method to approximate the root, aka solution, of this. So let's say we have x cubed plus 2x minus 3 equals 0. Now, these questions can be worded all kinds of different ways. This is one of the standard ways we can do it, but when we say approximate, we got to be more clear. How approximate do we need? So what we'll do is we'll do the following. So we'll approximate until we get 3 decimal places. So that's what we're going to do right now. So does anybody have a question about how we're going to do this, or not how we're going to do it, but what the question or the problem really is? All right, so here's a solution. Here's one way in which you can do this. So let's take a solution. So let's set f of x equal to x cubed plus 2x minus 3. And what do we know about that? We know that f prime is then 3x squared plus 2. So why am I taking this derivative? Because Newton's method tells me this is how I proceed. So we tried to illustrate what this was all about, the geometric stuff, on Tuesday. We drew some pictures. Now we're going to create a list of numbers. So how do we create this list of numbers? We need to start with a guess. So here's my sort of how I want to proceed. Next, you should note, what is f of 0? F of 0 is -3. And what is f of, say, 1? Well, f of 1 is equal to what? Zero. And of course, because we were creative, we are done. We found the root. What's the answer? Plug in 1, you get 0. Nothing to do.
Okay, so we're plugging the 0 into the original equation, not the.
No. See this? No, slow down. I am only plugging that in because it's easy to evaluate. Plug 0 in, what do you get? We're going to do another example in a second, but this is a very important problem here. I asked you to approximate a solution or a root.
Yes.
Is there anything to approximate? We actually found it. This was an easy equation to solve. You can solve it by inspection.
I was just asking, like, it's like, yeah, I just saw you plug 0 into the original one, so I didn't. All right.
No, that's not a bad question. But you're making a very common assumption that most students do. You are confusing plugging in 0 with finding roots. Those are two different things. F of 0 is not always going to be the same thing as what spits out 0. Notice here, when you plug 1 in, it spits out 0. So in order for me to make this lesson very apparent what's happening, let's do another example right away. So if I switch to the next page and I say, okay, let's repeat. Well, actually, let me go back because it's important you understand this. There's no need for Newton's method here. Now, I want you to think about this when we do this problem. So I'm going to alter the problem slightly. So let's repeat the last question for x cubed plus 2x. Now I'm going to do minus 5 equals 0. So here, f of x equals 3x squared plus 2, just like in the previous problem. Not f of x, f prime. Now, Josh, here's what I'm doing. I need to figure out where I think this root is. Like, where do I think it is? Do I think it's a big number? Like, do I think it's 52? Do I think it's -7? I got to figure out where do I think. I need a guess. So what I'm going to do is I'm just going to do some investigating very simply. I am going to note that f of 0. Why am I taking 0? Because that's easy to plug in. If I plug in 0, I get -5. So if I'm going too fast, maybe let me remind you what I'm using for my f here. So let me get a green. I am calling this guy right here, this left-hand side, I am calling this f of x. I'm giving it a name so that I can use calculus. All right, now, why am I taking the derivative? Well, because as we showed you on Tuesday, the way to do this is to analyze the function and its derivative. And we can't do that till we have an idea of where the root is. So my eyes say, okay, if I plug 0 in, I get a negative output. And then let's pick another simple thing to plug in. How about 1 or 2? And what happens when I plug in, say, 2, is when I plug in 2, I get 8 plus 10, excuse me, 8 plus 4, which is 12, so I get 7. So the IVT, the intermediate value theorem, says that the root is in the interval -5 to 7. That's what it tells us. We know it has to be between the two because one endpoint is negative and the other's positive. So somewhere I have to cross 0. So this gives me an idea of where to guess. I just need to guess any number between -5 and 7. Why not choose an easy number like 1 or 2? Does anybody have a question about this? I am trying to use deductive reasoning to figure out what a good guess is. Okay, so our guess should be a number in this interval. So for simplicity, let's choose 1. So remember, we call this guess x sub 1. This is our guess. Now what we're going to do is we're going to do this geometric construction. We find tangent lines and we solve their roots, and then we do it again and again. And there's a very systematic way of doing it. And so thus, what is our next guess? Our next guess is given by the following equation. We have to take this, which in this particular problem is 1 minus f of 1 divided by f prime of 1. Now, the easiest way to do this is to use a calculator.
From last night.
The easiest way is to go to something like Desmos or use a handheld calculator. I don't care what you use, but you gotta, if you don't want to do it by hand, then you should use a calculator. So remember, our function is f of x, or x cubed, excuse me, plus 2x minus 5. And the derivative is 3x squared plus 2. So you can plug these things in. To a calculator. An easy way to do this is to use Desmos. It's very effective because you can just tell it what f is. Oh. So if I plug 1 into this expression, what do you get? Well, let's do the first one by hand so we're all clear. When I plug 1 into the original function, remember the original function is 3x squared plus 2x minus 5. So when I plug 1 in it, I get -2. And then when I plug 1 into the derivative, I get 5. So if I do the arithmetic here, I have 7/5. Of course, we can write this as a decimal to get a better feel for its value. So 7/5, if you ask yourself what it is in decimal, is 1.4. So does anybody have a question about this? Now, what I'm going to do in order of to save time is I'm going to do these calculations using a calculator now because you guys are capable of doing this. And the only way to learn how to do it is to do it. And when you do on your own, you will learn different sort of little shortcuts or ways that you can do it. You can also, for those of you who are familiar with how to program, you can easily write a for loop to do this. because all you're doing is repeating the same thing over and over again. We're going to see that in a second. Does anybody have a question about this so far?
So when we repeat, right, we use the same function, the same derivative.
Use the same f and the same derivative, yes. So now let's do it. Let's write it out. So now we repeat. So now we want to find, we found x sub 2, now we want to find the third one. So that is x sub 2, the previous guy, minus f evaluated at the previous guy, over f prime evaluated at the previous guy. So this is 1.4 minus f evaluated at 1.4 over f prime of 1.4. And if you do this calculation properly, you will get 1.3309645. So what you need to do is make sure that you get the same numbers that I'm getting. How do you do that? You go to a calculator. So does anybody have a question about this? Okay, so what we can do is we can repeat this process again. So let's go to the next page. So we repeat a few more times. So let's think about our list. What we end up getting is we get our x sub 1, our first one was 1. Our x sub 2 was 1.4. Then we got, for x sub 3, we got 1.3309645. Now, if I do that again, I get 1.3282728. And then if I go again, I get 1.32828. So what you'll see is I am now accurate to 4 decimal places after just 5 iterations. So they agree on first 4 decimal places. And so we have now succeeded in what the original question asked. The original question asked, what is the root? And use Newton's method to get it to at least, what did I say, 2? What was it? 3 decimal places. So I said 3. We got 4. Now, if you use it a different initial guess, it might take you longer or it might take you shorter to get here. Does anybody have a question?
No.
So here's what we can conclude. We can conclude the following just from what we did. This simple calculation is very, very useful because it tells us this. So we conclude the root R is approximately what? Well, it's approximately 1.328. So we know that much, and we're excited. Now, if you happen to go to a calculator that graphs and you graphed F and you zoomed in where it crosses the x-axis, so if you went to Desmos and zoomed in, you would see that we get the same answer the calculator gets. 1.328 is the actual root. Does anybody have a question about this? Questions? Now, again, this is something that you can, if you play around with Desmos, you can figure out a quick way of doing this. But this algorithm is not difficult to do using a computer. So if any of you have sort of, how do you say this? If any of you have any sort of experience with basic programming, it's about 3 lines of code to generate this. So maybe what I'll do is I'll write up how to do that, and I'll put it on Canvas for like an extra credit assignment if anybody wants it. It's a very good, if you've never written code before, it's a great way to learn how to code because it's real simple. And if I can do it, you can do it. Trust me. Okay, any questions, comments, concerns? Anybody want to start a fight saying they hate math? Oh, there's 15 of you now. That is so cute.
So when we do let's say when you give us a practice set and then you give us this question, so do we have to show the workout for every X?
Oh, no. So that's a good question. So most of you could just cheat if you wanted to. If I said use Newton's method, you could just, I guess you're asking, can I just write down this final list, this little table? Sure, you could do that. But I could also phrase the question that forces you to do it by hand. I can say, show the details, right? The point is in order to learn how to do it, you need to do it by hand. But once you learn how to do it, you realize that all the computation can be done using the machine. So I could ask you to analyze Newton's method, or I could say write down Newton's method. But if I ask you to solve using Newton's method, then you could easily just do what I did. Use a calculator to do all the calculations.
Okay.
Yeah. One other thing that there is a caution, and I'm going to write this on the next page because in the real world this could happen. So I want to make sure you guys are aware of it. So let's caution here. There are times that Newton's method doesn't work. So we don't study those in this class, but it is possible that if you try to use Newton's method, it doesn't work. So what we do is the word some people use is pitfalls, but we'll say we ignore these quote unquote pitfalls in Calc 1. There's other courses where you can study all this stuff. The book talks about it if you're interested, but I'm not worried about it.
You give an example of a function.
What word fails?
Yeah, just a function.
Just think about any type of function that would have bad behavior. First off, if you can't take a derivative, it would fail. If the function has a certain type of concavity, it wouldn't converge. I mean, think about, a good way to think about it is to think about functions that have bad sort of types of behavior. If you have asymptotes, for example, if you have a discontinuity, those are ways to think about it. Trying to think of what else off the top of my head that you would maybe understand. So here's an example to see what would happen. So these happen with sort of bad guesses. asymptotes. Etc. So a standard example is the following, if you're interested. I'm not going to test you on this. So if you take this function, take something, you need something that has an asymptote or like a discontinuity. So let's take something like 8x squared over, say, 5x squared plus 1. Or maybe not 5. Let's say, okay. Well, okay, no, let's not use 5. Let's be more, we'll make sure we get the good pattern here. So if I use 3 here, and then if you take your initial guess to be x sub 1 equals 1. So if you want to learn the pitfalls, do this and see what happens. So try it with 1. And then also try it if you try it with 1, you might get 1 answer. And then you could try it with something different. Maybe instead of doing 1, you do 1.1. So basically what you'd have to go through this experiment yourself if you wanted to see what happens. It's worth checking out if you're interested.
As you hear Dr.
Is that a question? What is that? Someone have a question? All right. I'm assuming that was someone's microphone. So anyhow, if you're interested in the pitfalls, so Joel, you said, so Joel had a question about number 6. Well, that's 2 different problems. Number 6 is not Newton's method. Number 6 is an optimation problem. So if you look at the homework, number 6 has nothing to do with Newton's method. I am telling you, you can use Newton's method to solve the equation. I'm not saying you have to, though. Newton's method could be a tool in problem 6, but it doesn't have to be. So if you took the correct distance formulas, derivative and stuff, then you don't, that's the goal. Set it equal to 0 and solve. I don't know. Did that answer your question?
So that's all function equal to 0 when we use the Newton's law.
Oh, so again, here's the problem. You guys are confusing 2 things, it seems to me. Newton's method is a tool for solving equations. It is a tool for solving equations. That means that sometimes it could be used when you're finding critical numbers. But finding critical numbers doesn't always require Newton's method. So do not get confused with finding critical numbers and using Newton's method. They are 2 different concepts. One can be used to assist in the other. Newton's method is merely a tool for solving equations. So let me spell that out very, very carefully. Remark, Newton's method is a tool for solving, and I will put solving in quotations because you're not necessarily solving, you're approximating. You're solving equations. That is the key to understand. It has nothing directly to do with optimization. So what you're doing is you're getting 2 concepts that aren't necessarily related. You're getting them confused, and you don't want to do that. You need to think of them as 2 entities.
It's just like it's just the same way like a quadratic equation, right? Something similar but not the same.
Right. It's okay. So there you go. The quadratic formula is a tool to solve certain equations. So there you go. Just like the quadratic formula is a tool for certain equations, namely quadratics. You don't use the quadratic equation on every single equation, only when it applies. All right. So again, and by the way, here's another and very important thing, the O'Grady dead horse that he beats over and over and over again. That you guys are never, ever, ever going to learn this stuff unless you accept the fact that it takes more than 10 minutes to learn these topics. Calculus is an extremely difficult subject. And as I've said before, not only is it extremely difficult, we are squishing all kinds of information into a short amount of time. So the learning does not necessarily come from, you're not going to watch me do 2 examples and say, oh shit, there it is, I got it, it's easy. That's not how this works. The learning is happening later today and tomorrow and the next day when you're studying and trying to solve a problem for 20 minutes or an hour and you keep getting it wrong and then you finally get it right. That is the learning. You learn this by doing. And the thing that really stinks about calculus is that you often get it wrong in the beginning more often than you'd like to. Oftentimes you have to get it wrong a few times and then have someone help you or have you see the light by watching a video or looking at the examples we did in class 5 times. That's when the learning happens. It's not going to happen in 45 minutes or an hour and 20 minutes of us watching a Zoom lecture. I wish it were that way. I wish there was a pill I can say, hey, go and do this. And tomorrow, if you take this pill, you'll wake up and you'll be great at calculus. But that's just not how it works, unfortunately. And for that, I apologize, but that's life. Does anybody have a question about that? Because we're about to do a new topic now. So just, everybody says, that's not fair. I can't do multiple topics. Such is life. You guys can all write a letter to the powers that be and say, I hate calculus. It's too hard, and see if they get rid of it. Maybe they will. Maybe they'll no longer make you take calculus. Okay. Okay. So let us move on then. By the way, you might say, well, what does all this stuff have to do? Well, these are all applications of the derivative. The applications of the derivative, optimization, tangent lines, these are all related. A good thing for you, a good barometer is for you to really think about how this is related. I mean, look at Newton's method. Look at the formula. How is that related to tangent lines? How is that related to what we've been doing the past few classes? It's all very much related. Okay. Moving on. Fun times. So, our final application of differentiation. I guess I should learn how to spell. Of course, you guys know that I can't spell, so that's okay. We forgive one another. So our final application of differentiation is what's called L'Hopital's rule. So L'Hopital. So we're gonna write this down in a second. So L'Hopital was a mathematician. He's often credited with the first calculus textbook many years ago. So what is L'Hopital's rule? So let's remind you that this is, let's do phonetics. I love to do phonetics. Phonetics are fun. So this is low P tall. L'Hôpital. L'Hôpital. So what is L'Hôpital's role? L'Hôpital's role is another toll. So this is a toll for computing some, not all, some limits. So here's the general idea. We're not going to get into specifics, but let's look at the general idea, and then we'll show you how to use it, and we'll be very happy, and we'll move on. So to motivate, consider limits of the form limit as x goes to a of one expression divided by another expression. So imagine a limit, and you've seen many limits in this class that are the ratio of two expressions. That's what I'm saying right here. We got an f, some expression we're calling f, and then some expression we're calling g. Okay. Using the linear approximation, oh boy. Using the linear approximation of f and g, we might expect the following. We might expect that this limit is somehow connected to the linear approximation. So what is the linear approximation? Let's remind ourselves of that. So what is linear approximation? Well, we might expect that the limit as x goes to a of f of x over g of x, we would expect perhaps that if we replaced f and g with their approximations, it would be true. Now, what is their approximation? The linear approximation of f of x is f of a plus f prime of a times x minus a over g of a plus g prime of a over x minus a. So if we take the linear approximations, we would expect these two limits to be the same. Okay, so you might say, okay, the left-hand side doesn't look as bad as the right-hand side, and I agree. The right-hand side has more nonsense. But if we take another assumption, if we say, okay, what are most limits that we studied? What is the big issue with most of these limits? So if you ignore the right-hand side of this for a second, and you say, what was always the issue? What happened? When you plugged in the limiting value, you ended up getting division by what? 0. So that was a common theme in a lot of these limits we did. And a lot of these limits, when we plugged in the value for a, we got something divided by 0. So let's assume, because that happened a lot, let's assume that, let's use green. So let's assume that f of a equals g of a, and they are both 0. Well, then the above becomes If we assume that, then it disappears. So if I take my red and just strike this out and strike this out, I say, sweet. I get that the limit as x approaches a of f of x divided by g of x. I get that this is the limit as x approaches a of f prime of a over g prime of a. And then this is x minus a. This is a product, and this is times x minus a here. And you learned way back in middle school that you can cancel common factors. So this and this disappear. And so what we've arrived at is a very, very useful formula that we think should be correct. And in fact, it is. So before I go to the next page, does anybody have a question about this? Why did I cancel things out? Why did they disappear?
So why did you actually cancel things?
Why did I cancel what? Which ones? I canceled two things. Up top, I canceled f of a and g of a. I am assuming they're zero. If they're zero, why write them in? And then at the bottom, I have common factors. When you were in middle school, you learned to cancel common factors. That's how you reduced fractions. That's how you did all kinds of, you've done that since you started reducing fractions. That's called canceling common factors. If I have an x minus a upstairs and downstairs, well, that's just equal to 1. So we say we're canceling that. Now, does that make sense?
Yeah, it does.
Okay, so what's the sort of the consequence of all this? So, in other words, under the above assumptions, we expect this to be true. We expect that the original limit of this sort of quotient, we expect that it's actually equal to this limit. And this is actually true under the above assumptions. So it turns out this is true. And it's called, as we said before, L'Hopital's rule. L'Hopital's rule. So let's do an example, shall we? And if you have a question, please ask. So again, as you guys know, I'm not going to write down the details of this. Let's just do the example. If you want to see the specific statements of these theorems, you can read them in the book. Let's look at an example. So limit as x approaches 1 of the following. So let's say x cubed plus, I guess that doesn't make any sense. I gotta make it. So let's say x cubed plus x squared minus 2x over x minus 1. What is this limit equal to? So note, so if we quote unquote plug in x equals 1, we get 0 over 0. So this is called, doesn't make any sense, by the way. This is called an indeterminate. Why do we call it an indeterminate? Well, it doesn't make any sense. 0 over 0 is undefined. So L'Hopital says, the following. It says that the limit that we're after can be evaluated in a different manner. So what do we usually do so the reader knows what we're doing is over the equal sign, I like to put an L so everybody knows I'm using L'Hopital. And so then I'm going to differentiate the numerator, and I get 3x squared plus 2x minus 2. And then I differentiate the denominator, I get 1. And now I have no problems plugging in 1. When I plug in 1, I get 3. So we've now calculated this limit in a pretty quick way using this so-called trick of L'Hopital. Does anybody have a question about this? All right, let's do another one. So let's take the limit as x goes to 0 of, say, e to the x minus 1 over x. L'Hopital applies here because if I plug in 0, I get 0 over 0. So L'Hopital says take the derivative of the numerator, which is e to the x, take the derivative of the denominator. And you can now evaluate it. We couldn't evaluate it at first. So that's very important that we make a note of that. So note, if we set x equal to 0, what do we get? We get 0 over 0. This means L'Hopital does apply. Does anybody have a question about this? Okay, let's do another one. Examples are fun. It works if you're taking limits at infinity as well. So let's think about this. Let's say the limit as x goes to infinity of 4x plus 5 over 7x minus 3. So I'm allowed to take L'Hopital here as well because, and I'll explain this in a second, this is the limit as x goes to infinity of 4 over 7, which is just 4/7. Now, why does L'Hopital apply? Well, let's be very careful here. Let's make sure we see why it works. So note, if we quote unquote plug in infinity, what do we get? We get infinity over infinity. So this is also an indeterminate. So indeterminate just means it's an undefined number. So this is another shortcut for limits that we've been taking.
But how do we replace infinity over there? Like there is no variable.
Well, right. Okay, exactly. But notice that's why I put the words plug in quotations. But what happens to the expression 4x plus 5 as x goes to infinity? It also goes where? Infinity. And what about the denominator? If you replace x with very, very large numbers, 7x minus 3 is also a very, very large number, right?
So, will we ever actually need to plug them in, or this is just like a what if?
No, well, you can't plug them in. It doesn't make sense. That's the whole point.
Okay.
So, but L'Hopital only works when you get infinity over infinity or 0 over 0. So there are times when you can use L'Hopital illegally.
So is the answer here 4 over 7 or?
Yes, the answer is 4 over 7. Look, if
Infinity over infinity is not the answer, right?
no. Infinity over infinity, again, it doesn't make sense. Anytime you write infinity over infinity, you're writing something that's undefined. You're making something up. Doesn't make sense. When you write 0 over 0, you're writing something that doesn't make sense. And the name we give for that in math is we call it indeterminate. It has no definition. There's no way to define it. However, if you went to Desmos and graphed 4x plus 5 over 7x minus 3, what do you see happening? You see you have an asymptote at 4/7. You don't believe me, go check it out. Okay, let's do another example. This is important as well to help illustrate this process. So sometimes we must do some algebra before applying L'Hopital. So let's look at an example of this. Suppose I want to compute this limit, the limit as x goes to 0 of x times the log of x. So if we plug in, again, if I plug in, it doesn't make sense to do this, but if I think about this, if I ask myself, what is happening as x goes to 0, what do I get? You get 0 times log of 0, which is equal to 0 times negative infinity. This makes no sense. That's the point. It's indeterminate. It makes no sense. There is no way that a human being can define what it means for 0 times negative infinity. Now, the difference is if you went to the graph and looked at the graph of x log x, you would see that it is something happening there. There is a behavior, and we want to figure out what it is. So go to Desmos. If I go to Desmos and I say, okay, O'Grady tells me something's happening, let me see. So if I graph y equals x log x, and I show this to you, if I go to my, and I don't know if you guys can see this, but can you guys all see Desmos now? Hopefully.
Yes.
This red curve is the inputs go to 0, this output. Where's the red curve going? It's going to 0, right? It's going there. Something's happening. The graph is going to 0, which means we are not analyzing this correct when we make this nonsense of 0 times negative infinity. We have a war happening. You have the function x, and it's going to war with the function log x. We need to know who's going to win. X wants to go to 0. Log x wants to go to negative infinity. That's what this means over here. There's a war, and we need to figure out how to determine who's going to win. Okay, so how do we do this exactly? How do we go about deciding who's going to win? Well, L'Hopital is the answer. So to use L'Hopital, we're going to rewrite. So if I have x log x, another way of writing this is log of x divided by 1 over x. Then, if we set x equal to 0, we get the following. We get log of 0 over 1 over 0, which in a ridiculous statement is negative infinity over infinity. And this is an indeterminate. It makes no sense to say negative infinity divided by infinity. That has no meaning. But anytime we have the infinity divided by infinity or 0 divided by 0, anytime that undefined thing pops up, L'Hopital gives us a way to handle that. So we can apply L'Hopital. Does anybody have a question about this?
No.
All right. So now L'Hopital applies. And by the way, what happens is you guys forget your basic algebra. Some of you are looking at this equation up here like, what did he do? Well, all I'm doing is I'm just rewriting multiplication as division. You do this all the time. Multiplying by 5 is the same as dividing by 1/5. Multiplying by x is the same as dividing by 1 over x. Okay, so now we have to do some fun stuff. So we compute. The original limit we're after which is x log of x. This can be rewritten as the limit as x goes to 0 of log x over 1 over x. And we can apply our friend L'Hopital. So now we have to take the derivative of the numerator, which is 1 over x, and the derivative of the denominator, which is negative 1 over x squared. That is basic derivative formulas. So if I come over to the right-hand side, let's just remind you of that so you don't have heart failure. So recall, if I take the derivative of the log, that's 1 over x. And what is the derivative of 1 over x? Well, we did that a long time ago. That's negative 1 over x squared. So that's how I'm getting that line right after the L'Hopital rule. Okay, so now it becomes just some cancelization. If I come over here, this thing simplifies all the way down to what? Well, 1 over x divided by 1 over x squared is nothing more than negative x. And so if we now can finally plug in 0 and we get 0. So if you need some verification for that other line, let's do that. So 1 over x divided by negative 1 over x squared. You learned this in 5th grade. This is 1 over x times negative x squared over 1, which is negative x. Whew, that was fun. Now, I know you guys like to have context, and I do too. So before I give you some context, does anybody have a question about this? Okay, so these examples are, again, these are textbook examples. You should practice them, know how to do them. Some context for this. You know, I've used this example a lot, but in computer science, in the theory of computer science, we're always interested in how long it takes algorithms to run. Are they polynomial time? Are they logarithmic time? Are they exponential time? Right now, you're studying, or you're hearing all this stuff in the news about growth rates of this virus. How does it spread? Is it exponential? Blah, blah, blah. The way we analyze these growth rates is using limits. We use L'Hopital's rule. So if you're thinking, oh, this is stupid, I'll never use it, well, maybe so. But then some of you will analyze algorithms later, or maybe you'll analyze data and you want to know what kind of growth rate you have. The way we describe growth rates is through these things called limits. Well, at least it's one way we do it. And many of you will eventually get to learn about more details of this analysis, like big O notation. This is something done in polynomial time. Is it done in logarithmic time? Is it done in exponential time? So some of you will get to study growth rates, and one of the ways you do that is using L'Hopital's rule. So there you go, context. Anyhow, does anybody else have a question? This was so much fun. I will assign some practice problems. I'm saving the whiteboards now. I will put those on Canvas, and then I will try to get these lectures up on YouTube or something as soon as I can. It's taking longer than I anticipated, though. Okay, if you guys don't have any questions, then I will end, as they say, This class has ended. You may go in peace.
So what time do you have a class tomorrow?
What time do I what?
Do we have a class tomorrow?
Oh, yeah, we will have. Oh, that's a good question. So here's what's going to happen on Fridays. I am going to do class at 10 o'clock on Fridays. And then I will upload. I will not do a 1 o'clock. Now, if you guys absolutely want me to do a 1 o'clock as well, I will do that. But it's kind of hard for me to do both just because of all the chaos in my house. Now, I can make arrangements to do a 1 o'clock, but I mean, I think it's just the same as if everybody joins at 10 if they can, and otherwise I'll just post the lecture to the internet for you to watch.
How about if we do it like around 11, but only one class?
No. I have class will be at 10. I
Okay.
can't do it at 11. I have another class at 11. So I have class at 10 tomorrow. I have a class at 11 and at 12. So it's just much easier for me to do one section of Calc 1. I know. And again, if you guys hammer my email and beg for a 1 o'clock one, I'll do a 1 o'clock one. But it's kind of difficult for me under these circumstances. But I can at least do the 10 o'clock one, and I would be happy. You know, even if you can't make it, just log on, and you can just have it on your computer, and then you can watch it. I mean, I believe you guys have the ability to save it, don't you? Can you record on your own computer, or do you have the option to record?
Yeah, we can record, but we need your permission.
Well, I don't care. Does it ask me for your permission? Okay, you're more than welcome to do it. I don't care. So look, we'll handle it like this. Tomorrow at 10 o'clock, I will do the lecture. There's a 10 o'clock code. You guys know that it's on, I gave you, you're going to need a different code for, not a different code, the different link for tomorrow morning. It's on Canvas. I posted it last week. What's that?
How do you actually request? Because you have to request permission. Like,
yeah, I don't know why it's doing that. I don't care. What does it say if you request? How do you do that? I'll have to look into it. I don't know. I mean, I recorded it already, so I'm just saying if you're not able to watch actually at 10 a.m., but you want to see it before I upload it, I don't see why you can't just record it yourself and then go watch it whenever you want. I don't know why I don't see. I'll have to look into how do I give you permission. All right. I'll try to figure that out. Maybe someone knows they can share with us. I don't see on here how I can do that. It says auto accept all. Is this which? Oh, so you want that. Okay, so you want to share. See, I don't understand this. See, what is happening? I don't know. I'm going to have to look into this. And then once I think I accidentally hit the wrong button, show, but I apologize. I'll look into it. I'll see how you record. Does anybody else have any questions?
No.
All right, so tomorrow we'll do more examples, and then we'll set the stage for what's next. So hopefully you can all join at 10. If not, I will upload it so you can see it over the weekend for sure. All right, I am officially stopping the recording.